Hello again, Math 10Cs. In today's lesson, we're going to wrap up the unit on relations and functions. So I'm actually going to go through two lessons, both lessons 10 and 11. They're both quite short. They mainly just deal with problem solving, which we've already done back in, I think, lessons 5 and 6 in this unit. Except this time around, we're going to deal with the function notation as opposed to the XY notation we would have used in those lessons. Now, as you can see, I actually don't have a scanned copy of the lesson number 10. So I'm going to need you to be on page 477 in your work booklet, and you're going to need to actually just see the example problem there. And in fact, we're going to jump right to the example problem. We don't need to go through any new notes or material. We already have talked about function notation. Now it's a matter of just applying it to certain problems. So I'll start off by reading out the example to you. It says a candle manufacturer found that their long-last candles melted according to the formula H of T is equal to negative 2T plus 12, where H is the height of the candle in centimeters after T hours, so T be the melting time. A, I want to use the graphing calculator to sketch a graph of the function and show the graph on the grid to the right. And I just sketched a picture of what the grid would look like. Okay, the first thing we need to do is we need to take this equation in function notation and turn it into an equation I can plug into the graphing calculator. So this would look like, and I'll just turn this pen color to blue. Okay, so in function notation, h as a function of t is equal to negative 2t plus 12. Now, to turn this guy into the xy notation, h as a function of t is your output. It's the same thing as your variable y. And this would be equal to negative 2 times, well, your input variable would be time in this situation. And then the xy notation, your input variable would always be x. So you'd have negative 2x plus 12. Now, if I go to my graphing calculator and I plot it, I'm going to enter it as y1, and I'm going to show this in a second, is equal to negative 2x plus 12. Okay, so let's go to the graphing calculator. Make sure every other equation's been cleared from this. And we're going to enter negative 2x plus 12. And we're going to graph this. Okay, now that's not the greatest graph. I really want to try to focus in. I mean, generally when you sketch a graph, you want to be able to see both the x and the y intercepts. And also the picture of the graph on the page in the work booklet is really only focusing in on quadrant number 1. So what I'm going to do is I'm just going to tweak the window settings on my own to deal with this. So I'm just going to see like where I'm at on the graph right here. So I can see the x-intercept, no problem. Looks like the x-intercept is that x is 1, 2, 3, 4, 5, and 6. But the y-intercept is beyond the actual graph here. The graph goes up to a y maximum value of 10. So maybe we'll change it to 15. Okay, so what I'm going to do is I'll go to my window settings. And in the window settings, let's change the x minimum to 0. The x maximum you can leave as 10 because we could see that x-intercept. The y minimum will change it to 0. And the y maximum, we couldn't quite see the y-intercept. Let's change it to a little bit higher. So let's go to 15 and then take a look at it. Okay, let's see what we got now. Okay, that's not bad, but if we're going to use some of the calculator functions to get like x-intercepts or y-intercepts, we need to see both sides of the x and y-intercept. So I'm just going to go back to the window settings and change it so I can see a little bit of the left side of the y-axis and the bottom side of the x-axis. So going back here, let's change x min to negative 2, and then let's change the y minimum to also to negative 2. And if we graph this, okay, now I can actually see both sides of the y-axis, and I can see both sides of the x-axis. And that's going to be the graph that we're going to plot on our little on our little grid here. Okay, so let's go back now to the lesson. Okay, so you should label the graph. So on the y-axis, so again, y-axis is the same thing as h as a function of t. So we can label the y-axis as h as a function of t. And then your x-axis is being represented by the input variable of time. So we can write down time over here. Okay, I'm just going to take a line and I'm going to plot the graph. So I think our graph looks something along the lines of maybe it was like here. Oops. Kind of did something like this. Okay, and then if you want to, you can put those little arrows on the end, show the graph is continuous. Well, the graph's not going to have any physical meaning beyond the first quadrant. Okay, if I wanted to show what the window settings were, by the way, here's the way I could write this. So your X window settings, the ones I used were, I had an X minimum value of -2. I had an X maximum value of 10. And I had the X scale go up by 1s. And then the Y scale, I had go from -2 to about, I think it was 15. And then it also went up by 1s. Okay, so that's the first part of the question here. Okay, part B says determine the value of h of 5. Okay, so h of 5 just means take the equation h of t, which is -2t plus 12, and evaluate it when you plug in a value of t that is equal to 5. So, again, if you want, you can write the equation out again. So we have h of t would be equal to -2t plus 12. And we want to now calculate h of 5. So what h of 5 means is in the place of t, you're going to replace the t with a 5, and we're just going to evaluate this expression. So this would then be equal to 2 multiplied by 5 plus 12. And then you'd have h of 5 would be equal to 2 times 5 is 10 plus another 2. Oh, there's a negative in front of here. Oh, there we go. It'd actually be, yeah, just to point that out here, there should be a negative sign there. Yeah, so that would be -2 times 5 is -10, plus 12 would be +2. Okay, so h of 5 would be +2. So what this means right here is it's saying what is the height when time is 5 hours? So the height of the candle when the time is 5 hours would be 2 centimeters. Okay, let's go to part C now. Okay, part C says, oh, I just explained it. It says write in words the meaning of H5. Okay, so H5 is the height of the candle. And the height is your output here. The candle when your time is equal to 5 hours. Okay, this H right here, let's write the full unit out. Height of the candle in 5 hours. So it's melted for 5 hours. Okay, D says evaluate the following and explain their significance. Okay, so the first one we're going to do is it wants us to evaluate H of 0. Okay, so H of 0. I have no idea what happened there. That is not a bracket. Here. Try that again. Let's use a thinner pen. Okay, so it wants us to determine h of 0. And it says identify the significance. Well, let's calculate it first. Okay, so all we're going to do is we're going to take t of 0 and just plug it into this equation right here. So instead of like it being t, it's 0. We're going to evaluate the expression when t is equal to 0. So that would then be -2 multiplied by 0 plus 12. -2 times 0 is 0. Therefore, you'd have h of 0 is equal to 12. And then it says explain the significance of this. Well, h of 0 equal to 12, that is just going to be the height of the candle when 0 hours is passed. So that's actually the starting height of the candle, the original height of the candle. And actually, this is the y-intercept. Okay, so the y-intercept here would be, so your y-intercept, you have an x-coordinate that's 0, because that's your time value. Your time value is 0, and your height would be 12. And if you want to, you could actually label this on the graph here. You could say this is 0, comma, 12. That's my y-intercept. Okay, the second part of D wants me to determine h of 6. Okay, so h of 6, again, we're just going to take the equation h of t is -2t plus 12 and replace t with a 6. So we're going to evaluate that expression when t is 6. So that'll be -2 times 6 plus 12 would be equal to, well, -2 times 6 is -12. -12 plus +12 would just be 0. So you'd have h of 6 is equal to 0. Now, what does this physically mean? Well, that would be the time required for you to have no more of your candle left. The candle is completely melted. Okay, so I'd say time for candle to completely melt. Yep. Looks like my computer wants me to restart in 23 hours. Actually, have my computer force me to restart in the middle of parent-teacher interview, so that was great. Okay, I should also point out right here the time for the candle to completely melt. That is also the x-intercept. So the x-intercept would be 6, 0. If you go back up to the graph here, if you want, you could label the x-intercept. So the x-intercept would be 6, 0. So what that means is after 6 hours of melting, your height would then be 0 centimeters for the candle. Okay, let's go to part 3 now. So it wants h of 8. Okay, so once again, we just plug in t equals 8 into the equation. So that would be h of 8 is -2 times 8. And then we're going to add 12. -2 times 8 is -16, plus 12 would be -4. So you'd have h of 8 would be equal to -4. Now, what this technically would mean is it'd be what's the height of the candle after 8 hours? This doesn't make any sense. The height of the candle after 8 hours cannot be -4 centimeters, because that means that For example, if you had like your candle on top of a desk, it means the height of the candle would then be below the desk. That doesn't, again, it physically doesn't have any meaning in this context. So I'm just going to simply say by 8 hours, the candle is already melted. Therefore, h of 8 equals -4 has no physical meaning in the context of our problem. Okay, candle's already melted. All right, let's go to E. So E says, how long will it take the candle to burn down to a height of 7 centimeters? Okay, so now we don't know how long that is. So what's it's saying is like, what's the height of the candle? Or how long does it take for the height of the candle to be 7 centimeters? So I start off by writing the function notation like this. What this means here is the height of the candle after a time t would be equal to 7 centimeters, okay? And we're trying to figure out what that time value actually is. Okay, so here's how I do this. We know the equation tells me that h of t is equal to -2t plus 12. Now, we know here, or this is what we're trying to calculate, we're trying to figure out, like, at what time is the height equal to 7? So the height as a function of time equal to 7. So I'm going to take this h of t right here, I'm going to replace it with a 7. So this would then turn into 7 is equal to -2t plus 12. Okay, now we have a linear equation that we need to solve. So we're going to subtract 12 from both sides first. Subtract 12. 7 minus 12 will be -5. So -5 is equal to -2t. And then isolate the t by dividing both sides by -2. Divide by -2. And then your time would be a fraction, 5 over 2. But we'll just turn it into a decimal. And if you turn it into a decimal, 5 divided by 2 would be 2.5. And the units here are hours. So again, with the function notation, we start off by saying the height of the candle after a time t is equal to 7. We didn't know what the time t was, and then we solved for it. So now we know the height of the candle after 2.5 hours would be 7 centimeters. Okay, and then part F. Okay, part F says suggest an appropriate domain and range for the function. Okay, so let's start off with the domain. Now I'm going to use that little extra notation that I talked about in the previous lesson. So the extra notation you would use is, first of all, identify the variable being used to represent the domain. Well, if you look at the graph here, what's the x-axis? The x-axis is being the range of x values is going to be the domain. So we're going to use t as the variable. Okay, so we're going to put down t, and we're going to put this vertical sign here. Okay, and then we're going to do it exactly like we did before. Okay, now let's go back to the problem and make sense of this. So the domain is going to be you want to identify what's the lowest x value you can have and what's the biggest x value you can have. Now, the x value here is time t. So what's the lowest time value you could have? Well, it should be when time is 0, because you cannot have negative time. So the graph actually cannot exist like to the left of the y-axis. And then what's the biggest time value you can have? Well, that'd be the x-intercept, because once you hit the x-intercept, the candle is melted, and any time values past that don't mean anything because the candle is already melted. So what I would do then is for my domain, I would say the domain is your time would be greater than or equal to 0, but needs to be less than or equal to 6. And then from 0 to 6, time can be any real number. Now the range, so which variable are we using to represent the range? Now we're going to write it down in terms of the function notation. So the function notation, if you look at the y-axis here, we're using h as a function of t to represent the y-axis. So then this would be, we'll write down that variable, so h as a function of t, and then we'll put that vertical line down, and we'll go back to the graph and identify which values make sense. Okay, so what's the smallest value the height of the candle could be? Well, it'd be 0, okay? And what's the biggest value the height of the candle could be? Well, it'd be the y-intercept here. So the original height of the candle was 12. So if I go back to writing the domain down, it would then be your domain, it's not domain, your range. The height of the candle must be a number that's greater than or equal to 0, but has to be less than or equal to the starting height, which was 12. And then I can say the height of the candle is a function of time. So that's your output. The y variable can be any real number. Okay, and that's the domain. Okay, for this one, and we're going to go to the next lesson in a moment here. Okay, so the assignment questions to complete would be starting on page, the next page, which is page 478. Do numbers 1, 3, and 5. So I was going to assign a few from each of the lessons. Okay, let's go to, this is essentially just more examples of like different word problems here. Okay, so we're going to go to lesson 11 now and kind of just wrap the unit up. Okay, so what do we have? It says the Carter family are driving to Yukon for a family vacation. The graph represents the amount of fuel in liters in the gas tank of their car on their first day of the journey. So on the y-axis, we have the amount of fuel in liters, and on the y-axis, it identifies the time of the day. So they're starting at driving at 7 o'clock in the morning, and this is based on a 24-hour clock, and they're going to drive until 1700 hours. 1700 hours would be 5 o'clock p.m. Okay, and it's showing different parts of their journey, like them going from A to B, B to C, C to D, D to E, E to F, F to G, and then G to H, and then H to I. Okay, what does it want us to do here? It says the graph journey is divided into 8 line segments. With reference to the journey, explain what is happening between these following points. Okay, so let's grab a pen. Okay, so let's focus on what's happening between A and B here. Okay, from point A to point B, it looks like your fuel, the amount of fuel in the car is dropping. So if the amount of the fuel in the car is dropping from A to B, it means you have to be driving the car. So what's happening is from A to B, we're driving, and specifically we're driving from 0700 hours to like 9 o'clock to 10 o'clock to 11 o'clock. So maybe what I could say right here to describe this is I could say that we're just simply driving. Okay, so I could say we're driving from 9 a.m. Oh, not 9 a.m. So we're starting at, oh my goodness, I cannot count. Okay, let's go back and erase this. Okay. Wow, how am I a math teacher? Okay. 7 plus 1 is 8. 8 plus 1 is 9. 9 plus 1 is 10. 10 plus 1 is 11. There we go. Okay. My goodness. Okay, so we're driving from 7 a.m. to, and if you look up at the graph here, point B ends there. So we're driving from 7 a.m. to 10 a.m. And we have a decrease in our fuel consumption at that point. Okay, now from B to C, you'll notice that the fuel consumption isn't changing. The fuel consumption from B to C is actually just sitting there at 20 liters in the gas tank. So what's happening here is that the only way that like in 1 hour, if like the fuel in your gas tank didn't change, it would mean that the car is not driving. So maybe they stopped to eat breakfast or something like that, okay? So I can say the car is not moving. Okay, so I don't know, I can make up what they're doing here. So I could say breakfast from 10 a.m. to, let's look right here. I think point C isn't quite at the 11. It looks at, that's about like 10:30, I think. So we could say it's eating breakfast from 10 a.m. to 10:30 a.m. Or maybe they decide to stop the car and everybody get out and just stand and stare into space for 30 minutes and then get back in the car. But you can come up with like your own descriptions as to what can happen. But the key thing is the car is not moving from that time period. Okay, now from C to D, let's look at what's happening here. Okay, C to D, we have this vertical line at 10:30. So what's happening now is from C to D, our amount of fuel in liters in the car is actually going up. So the only way that could happen is if they're actually like adding fuel into the car. So maybe after they got out of the car and they just stared into space for like 30 minutes, they decided to like finally fill up their car. So with gas, so I could say car filling with gas. Okay, and that happens like quickly. I mean, technically speaking, it wouldn't be a pure vertical line, but we don't need to worry about that. Okay, B says, what is the rate of fuel consumption in liters per hour between point D and point E? Okay, so we're going to focus on D to E here. Okay, D to E. Okay, so let's figure out how our fuel is the amount of fuel is changing. So at point D, okay, we have 60 liters of fuel in the car. And at point E, I think it's at 25 if we went all the way across here. Okay, so that's from point D to E. Okay, so we drop back down now. And I'll show you how to do a fuel consumption calculation in a moment. Okay, so from D to E, your fuel, so if you go from D to E, okay, your fuel went from 60 liters to 25 liters. So let's calculate that difference. So that would be 60 liters subtract 25 liters, which means that 35 liters of gas has been consumed. Okay, when you see that word rate, it means like it's a specific quantity over a certain amount of time. Okay, so I'm going from D to E here. So D was, we started at 10:30 a.m. Okay, and then 12 o'clock, 1 o'clock, 2 o'clock. So E is at 2 o'clock. Okay, so we are driving for from 10:30 a.m. to 2 o'clock p.m. would be 3.5 hours of driving. Okay, so 3.5 hours of driving. So to figure out the fuel consumption, all I would do is just take the amount of fuel consumed and divide by the time it took to do that. So that would be 35 liters divided by 3.5 hours of driving. 35 divided by 3.5 would be 10. And if we look at the units here, this would just be liters divided by hours. So that's my rate of consumption. So for every hour, we're consuming 10 liters of fuel. So that's my rate of consumption. Okay, it says which line segment represents the car being refueled for the second time. So again, when the car's getting refueled, it means you have an increase in the amount of fuel in liters. So that's going to be this spot right here. Okay, this spot is where you would have an increase in your the amount of fuel. Okay, so that's going to be from G to H, or we can just say GH here. Okay, D, calculate the total time the car is being driven. Okay, so when do they stop here? So they start at 7 a.m. And we end at 3, 4, 5 p.m. But it says just how long were you driving for. So what we do not want to include in this is we don't want to include the time where the car is actually like stopped, like when they're eating lunch or supper. So let's identify all the line segments where driving was occurring. So driving occurred from like point A to point B. Okay, point A to point B, I think was 3 hours of driving. And let's go back up here. When else are we driving? We're driving from D to E, and D to E was 3.5 hours of driving. $3.5 hours. And when else are we driving? Go back up here. We're driving from F to G. Again, you know you're driving because the amount of fuel in the car is going down. Okay, so that's from 3 to 4 o'clock, it looks like about. Yeah, I think so. Okay, 3 to 4 o'clock. So that's going to be 1 hour of driving. And that's from F to G. F to G, 1 hour. And then our final amount of time driving is going to be from H to I, so this point right here. So that's from 4 o'clock to 5 o'clock, which is also another hour of driving. So H to I would also be 1 hour. Okay, so to calculate the total time, just add these numbers together. So 3 hours plus 3.5 hours plus 1 hour plus another hour would give me the total driving time is 8.5 hours. Okay, E says if fuel costs 85 cents per liter, calculate the cost of the fuel used for the first day of the journey. Okay, so what this is telling me right here, let's turn this into dollars. So in dollars, this would be $0.85 per liter. Okay, now the way we want to calculate the total cost here is, this is really like it's kind of like a unit conversion problem where you got to like multiply different quantities together and get the units to cancel off, where the only unit I have left is dollars. But I can give you an equation you can use to calculate that as well. So your cost, the total cost would be equal to the rate of consumption multiplied by the driving time multiplied by the cost per liter. Okay, so let's multiply these numbers together. The rate of the consumption we got from part B, it was 10 liters per hour. Okay, so we'd have 10 liters per hour. Okay, multiplied by the driving time was 8.5 hours. And then multiplied by the cost per liter. So the cost per liter will be $0.85 per liter. Now, if you look at the units here, if a unit in like the numerator of a fraction, it would cancel off the unit in the denominator of a fraction. So this liters at the top right here would actually cancel off with this liters at the bottom. This hour on the bottom of the fraction would cancel off with the hours in the top here. And now the only unit we have left is going to be dollars, which is what we want because we want the total cost. And if we calculate this, multiply these numbers together, I believe it's going to give you $72.25. So that's the total cost. Again, you can use the equation, although realistically the way I came up with the equation is I just did like a simple like I just tried to cancel off all the different units. That's more of like a thing you do in science as opposed to math, like doing like a bit of a unit analysis. Okay, let's go to the second page. Okay, example 2. It says, suggest a possible scenario for each of the following graphs. Okay, so it says speed and time. So we can envision like having a car that's driving. Now let's identify all the different points here. So let's say this is like point A, this is point B, this is point C, this is point D, E, F, and then G. Again, this is more of like a physics question, identifying like what's going on with the motion here, but it's okay, we can play around with this a little bit right now. Okay, so speed is on the y-axis, time is on the x-axis. So at first, from point A to point B, my speed is not changing. It stays at the exact same number. So what I could say here is from A to B, the car is driving at a constant speed. So remember, maybe whoever's driving there just has the vehicle in cruise control where the speed of the vehicle is not changing. Okay, now B to C, I can see I have a decrease in speed. The speed goes down. So I can just simply say, car slows down. From C to D, again, our speed isn't changing, but it's lower on the y-axis. So would we be driving at a constant speed? Would we be driving at a slower constant speed? So I can say driving at slower constant speed. Okay, D to E, well, I'm picking up speed. So we could say car speeds up or accelerates. Okay, E to F, we're once again back to moving at a constant speed that's slower than the one from A to B and faster than the one from C to D. So I'll write it in comparison to what happened at C to D. So I'll just say car drives at faster constant speed than from C to D, or D to E. No, C to D. C to D is when we're at a constant speed. Okay, and then F to G would just be the car actually slows down and it comes to rest, because at the very end, like the graph actually hits the x-axis. So I could just say from F to G, car slows down to rest. Okay, B. This one's a little bit weird. So like what you have here is like you have an object that's initially not moving, then it starts to pick up quite a bit of speed. then it starts to slow down. Then an object it comes back to rest. Then it picks up a bunch of speed, is going really fast, then it slows down and comes back to rest. Picks up speed, comes to like a maximum speed, and then slows down and comes back to rest. Maybe the example I would give here is the motion of a pendulum. Again, this is really more of like a physics type problem. So you can think of it like this. Like maybe you have like, I'll sketch a little picture of a pendulum. Okay, so say you have like a pendulum. Okay, and we'll say this is point A. Okay, so I pull this pendulum back and I'm gonna release it from rest and it's gonna swing in this direction. So that would be point A on the graph here. So we could say this is point A. And then you let go of the pendulum. And then at some point down about here, that's when it would be moving the fastest. In physics, we refer to this as an equilibrium position. So here, point B, that's where you'd have your maximum speed. And then the pendulum would swing to the other side, come out to its maximum height, and then at point C here, it would stop for a brief instant, then it would start swinging back in the reverse direction. So this could be like point C on the graph. Okay, so maybe what I could just describe here is, I mean, there's other examples too, but you have like the repetitive motion, okay, where the pendulum keeps swinging back and forth, back and forth, back and forth. That's why you see the graph continue to repeat. So I could just say like the motion of a pendulum. But again, there are other examples. Okay, final one says, now instead of like it giving us a graph and we have to come up with the explanation, it gives us the explanation and we want to make a graph. Okay, so it says sketch a graph with no scale for each of the following. So it says the oven temperature when baking a pie. Okay, so presumably if I'm baking a pie, I need to preheat the oven first. So the oven is not going to start at 0 degrees Celsius. Like it's very unlikely your house is going to be that cold. I suspect the oven would be at room temperature to start off with. So room temperature might be a temperature on the y-axis that's a little bit higher up. So maybe what I would do here is, so I'll do a line. Okay, so the oven preheats to like whatever like temperature you're going to bake the pie at. So maybe it's like 350 degrees or something like that. And then you cook this pie at a constant temperature until it's done. And then you take the pie out of the oven and then you turn it off. So if you turn it off, then it would cool down. So then it would come back down to that room temperature. Again, I don't know if it's like perfectly linear in terms of like how the temperature goes up, but I could at least attempt to describe it here. So I could say, like, for example, this is preheating. So preheat, this is when it's baking. And then oven turned off. Okay, and then B says Ben taking part in a 100-meter sprint. So this time we would start at the origin on the graph, because like when you would start from rest. So maybe in this one, what would happen is, so there's that first part in like your sprint when you're starting to move faster and faster and faster and accelerating. So I could probably represent that with like a line here. And then you get up to like your constant maximum speed. And then after you pass the finish line, you would then slow down back to rest. So again, there's a lot of different ways you can sketch these graphs here. So this would be your acceleration. This would be the maximum speed, maximum sprinting speed. And then this could be the person just slowing down after they cross finish line. Okay, and that's it. Okay, so for this lesson, so these questions start on the next page. So the next page would be page 483. Again, I'm just going to assign a few of them. So just 3 from each of these assignments. Let's do numbers 1, 3, and 7. Okay, and then that's it for the end of the unit. And then we'll figure out what the format a unit exam is going to take place in. Otherwise, I'll talk to you in the next set of lecture videos when we get into the unit on characteristics of linear relations, and talk to you then.